Hello, welcome and thank you for joining us on this very latest Prism Sound Wednesday webinar. Today we're going to be talking all about FFTs. We're going to explain what an FFT is and what it can be used for in the context of audio measurements. I'm your presenter for today. My name is Simon Woolard and I'm an applications engineer here at Prism Sound headquarters in the UK. Prism Sound is a professional audio solutions provider, and amongst other things we manufacture a range of digital and analog audio measurement solutions, and my role as an applications engineer is to ensure that our clients, prospective clients and others besides are able to use our solutions to solve their audio test and measurement requirements. So before I go through today's agenda, I'd like to involve you, the audience, and I want to ask you a question. So what I'm going to do is make an FFT measurement. I'm not going to explain the background, that will come later. I'm just going to simply turn my FFT trigger on in my measurement system, and there's a bit of averaging. I've now completed my FFT measurement. What I would like you to tell me is what you think this FFT tells us, and specifically I want to ask you what you think approximately is the noise floor reflected in this FFT measurement here. And those of you using a PC will see a survey question appear on your screen, and you have a number of options ranging from below minus 160 dBV to higher than minus 120 dBV. Perhaps you don't even know what the answer is. So I'd like you to consider what you think the approximate noise level is shown in this measurement and send me the answers. There is then a second question, just asking you for a little bit of feedback about what audio measurements you have made in the past, and that will help me to understand a bit more about you, the audience that I'm talking to today. Those questions, the survey, completely anonymous, so we won't be shaming anybody if they get the answers incorrect or if they appear to be inexperienced. This is really just so we can get a handle for the audience that we're talking to today. So I will give you a few more moments to answer those questions, and then we will take a look at how you have responded. So I shall bring that survey to a close now, and let's take a look at the results. Okay, so it's confession time from me. I've deliberately laid a trap here for you, and the answer that I wanted you to give me was minus 140 dBV for the noise level in this FFT measurement. That answer is actually incorrect. I can show you what the correct answer is. In this case it is minus 111 dBV. Now, I'm not going to give the game away and tell you why it's not minus 140. I'm going to save that for later. We need to build up a little bit of background theory first before we can tackle this question. Looking at the responses to the second part of our survey, it looks like we have a good range here of people who have some experience making various different types of audio measurements, like distortion and noise and frequency response and crosstalk. Actually, all of these things can be derived from FFTs, but we need to be a little bit careful, and we're going to spend some time talking about the background theory before we move on to the real-world application of FFTs in the field of audio measurement. Okay, so this is the agenda for today. First of all, I'm going to spend a little bit of time talking about the FFT algorithm. I see from our survey that some of you are new to audio test and measurement, so we need to make sure that we've covered a bit of background theory here to bring everybody up to speed. And discussion of the FFT algorithm inevitably leads to discussion of time domain window functions, and again I'll explain all about that when we get there. I'm going to spend a bit of time talking about FFTs of bin-centered and arbitrary frequency tones, and then we'll spend some more time discussing the issue of interpreting FFT results and coming back to the question of why the answer in our previous survey was not minus 140 dBV. We'll spend a bit of time looking at how we get the optimal results out of our FFT measurements, and then we'll talk about how we can go about extracting some of those audio parameters that some of you are familiar with measuring, like noise, harmonic distortion, crosstalk, from our FFTs. So that's the agenda. Let's get stuck in. Let's talk about the FFT algorithm first of all. What does it mean? Well, in short, it's an abbreviation for fast Fourier transform. And in essence, it is a digital signal processing tool that allows us to transpose digitized time domain data to the frequency domain. What does that mean? Well, it allows us to translate a time domain waveform. The example I've shown here on screen is a green sinusoidal waveform. Allows us to transpose that into the frequency domain and reveal the spectrum of that time domain signal. Let's just spend a little bit of time considering a couple of cases that will allow us to understand what we mean by these two different representations, the time domain and the frequency domain representation of a signal, whether that's audio or video or anything else for that matter. So here I've taken a signal in the time domain that, well, I'm saying it's infinite. Obviously, I can't show you an infinite duration signal, but if we take, mathematically at least, the hypothetical case where we have an infinite duration sine wave, its equivalent in the frequency domain is a very narrow, a perfectly infinitely narrow delta function in the frequency domain. So a broad event in time gives us a narrow event in frequency. And likewise, the inverse is true. An infinitely narrow event, so a delta function in the time domain, gives us an infinitely broad event in the frequency domain. So in other words, it contains all frequencies. And there is this reciprocal relationship between time and frequency, and the FFT process allows us to exploit that relationship between time and frequency domain to understand our audio signals in those two different contexts, those two different domains. So we actually have two tools available for this kind of analysis. One is called the fast Fourier transform, the FFT, and this, as we've discussed, transposes our signal from the time domain, so digitized time domain samples, into the frequency domain to give us a spectrum. The inverse FFT, or the IFFT, does the opposite. It transposes from the frequency domain into the time domain, so it takes a spectrum and gives us the equivalent time domain signal associated with that spectrum. Okay, so that brings us hopefully up to speed on what the FFT is and what it does. Why do we use them? Well, the spectrum is actually potentially very useful to us. The FFT algorithm is very powerful and allows us to reveal minute low-level detail in the spectrum of a signal that isn't visible in the time domain waveform. All we can really see in this example here, in the green trace, is a sinusoidal signal. That's about the level of detail that we can establish from that particular realization of the signal. The spectrum, on the other hand, gives us potentially a lot more information, and we can see that in addition to the 1 kHz fundamental here, we can see information relating to the harmonic distortion products. We've got some intermodulation sidebands here either side of the fundamental, and we've also got some intermodulation artifacts happening at a higher frequency as well. And these low-level artifacts are easily revealed in an FFT spectrum, but are, for all practical purposes, invisible when we look at the time domain signal. Okay, I want to talk about the FFT algorithm itself. Now, I don't really want to get too deeply into the mathematics here, but I just want to show you this this formula here, which is used when we perform an FFT calculation. And there's one aspect of this in particular that I want to bring to your attention, and that is that a fast Fourier transform requires an integration, a summation, over an infinite time period. And of course, in the real world, that's infinitely impractical. So what we do when we employ the FFT process, the FFT algorithm, is we use a truncated version of our time domain signal. So in other words, we don't integrate over an infinite time. We only take a finite number of samples of our audio signal before we then perform the FFT process. This truncation, this selectively choosing a finite number of samples in the time domain, actually modifies the resulting FFT spectrum. And we'll talk about that in a little more detail in the next section. But in basic terms, the process of performing an FFT involves selecting a number of samples, and the fast Fourier transform algorithm requires that we take a power of 2, so 2 to the n samples, where n is an integer, and then we perform our FFT process, and we end up with 2 to the n minus 1, or half as many points, bins, in the frequency domain, in the real frequency domain, I should say. Okay, so let's take a look at window functions now, this notion of truncating our potentially infinite duration signal to a manageable size. So imagine again that this is my continuous sine wave starting an infinitely long time ago and continuing forever into the future. Even the most patient audio engineer on the planet doesn't have enough time on his hands to be able to perform a measurement on an infinite duration signal. So we have to truncate this signal, take a smaller chunk of it, a smaller portion in the time domain before we can perform our FFT. And the most basic, the simplest way of truncating this signal would be to use what we call a rectangular window function. So just simply taking a number of samples starting at time t equals 0 and finishing 2 to the n samples later. Now, as I've attempted to illustrate in this diagram here, the truncation process, the windowing process, effectively modifies the signal and its resulting FFT spectrum. And you can think of it one of two ways. In the crude visual way that I've illustrated on screen, there is effectively a discontinuity between the start of this buffer and the end of this buffer. Mathematically, what happens is that this multiplication, this modulation of the signal by the window function effectively translates to a convolution in the frequency domain. So the spectrum of the signal and the spectrum of the window function are convoluted in the time domain. And don't worry if you're not too familiar with the terminology, we'll take a look at exactly what that means in just a moment. Okay, so the rectangular window is non-ideal in many cases, so we might need to use a slightly better window function, and a very simple modification might be to make this triangular window function instead. So we reduce the effect of these discontinuities at the beginning and the end of the buffer. That does offer us some improvements, but it's still not an ideal window function, and I don't really want to get into the maths here. I want to show you something a little bit more practical, so let's actually take a look at some measurements and see what I mean by all of this. So I'm just going to open a new file here. What I'm doing here is I'm generating a sinusoid, so I have a sine wave in my signal generator. I have an amplitude of 1 dB below full scale, and my frequency of my sinusoid is 1000 Hertz, 1 kilohertz. I'm actually capturing 4096 samples in the time domain. I'm applying a rectangular window and performing an FFT. So the resulting time domain trace is here on the lower portion of the trace window. You can see that this is our sinusoidal signal. And in the red upper trace here, we have our resulting FFT. And we can discriminate the sinusoidal component here. There's a clear peak in the FFT spectrum at around about 1 kilohertz where we'd expect it. But the FFT doesn't really show us anything more than that. There is insufficient dynamic range with this particular combination of signal and window function to reveal anything useful about the signal. So let's try the triangular window then. I'll open this pre-configured file here. The rectangular case, the rectangular FFT is shown in grey, and the new updated live measurement is shown here in red. And you can see we do get an improvement in analysis dynamic range, but it's really not sufficient to allow us to do anything useful from an audio perspective, to do things like measure noise and distortion and crosstalk and all those other things that you're used to measuring. So one additional example here then, I have what is known as the Prism 7 window function that I've selected from my FFT parameters here. And now we see in the red live FFT trace far more useful information. We can discriminate not just the fundamental here at 1 kilohertz, but we can see each of these discrete harmonic distortion products right up to very high frequencies. And we haven't really yet done anything to optimize the resolution of this FFT, but already we're seeing quite a lot of detail here with a very small, or modestly small, FFT size. So in general terms then, we have a number of window functions available to us, and I've just opened a new file here showing you a number of measurements that I made prior to today's session. On the lower portion of the trace here, I've just shown you all of the window functions that I've used to perform these various FFT measurements in the upper half of the trace here, and the colours are matched. So for example, the rectangular window is red on both halves of the diagram here. Now what you can see is that there is a very large range of performance in these various different window functions for what appear to be relatively modest differences in behaviour in the time domain. And what we tend to find is that there is a trade-off between the analysis dynamic range, so that the ability to resolve these low-level noise and distortion products, and the spectral leakage of the window function. And we can't have both. We can't have absolutely perfect dynamic range and absolutely no spectral leakage. But what we can do is we can find a good compromise. And what we at Prism Sound have done is designed a series of window functions through some fairly sophisticated optimization algorithms that give you the best trade-off of analysis dynamic range and spectral leakage specifically for audio applications. And this pink Prism 5 and this white Prism 7 window are the two window functions that we use most commonly in audio measurements, at least when you're using the Prism Sound tester measurement solutions. What we do notice is that there is a small difference in the amount of spectral leakage between these two window functions. So the Prism 5 window, if I were to just turn off these other windows for a second, the Prism 5 window gives us 5 bins of spectral leakage either side of our fundamental. 1, 2, 3, 4, 5. The Prism 7 window function gives us, you can probably guess, 1, 2, 3, 4, 5, 6, 7 bins of spectral leakage either side of our tone components. So there's a brief tour of window functions. What I should have explained actually, I was making those measurements on an external D to A converter FX unit. So we'll do some more measurements on this device a little bit later on. I want to keep the analysis fairly general. I'm not focusing too much on measuring any particular kind of audio device today, but I should have explained that we're using the D-Scope Series 3 measurement platform from Prism Sound, which has analog and digital inputs and outputs. So I was measuring a D to A converter, applying a digital input to the device and analysing the analog output. Okay, so having looked at time domain window functions, I just want to develop this idea a little bit further and talk about a couple of different specific cases of measuring pure tones, which is something that we do quite often in audio. We want to measure parameters like harmonic distortion or noise or crosstalk. Many of those tests can and frequently are accomplished using sinusoidal tones. So more often than not, what we want to do is use an arbitrary tone frequency. It might be 1 kilohertz, it might be 20 hertz, it could be any number potentially over the range of frequencies you want to measure. And generally speaking, you want to be able to dial in any frequency into your signal generator and perform your analysis. And we have already seen that for at least the 1 kilohertz case that I've illustrated, a rectangular window function is generally unsuitable for audio analysis because it doesn't give us sufficient analysis dynamic range to be able to see these low-level noise and distortion products that are interesting to us as audio engineers. So generally we tend to use an optimized window function like the Prism 7 window for doing audio measurements. However, as we have already seen, the window functions will introduce a certain amount of spectral leakage, the amount of which depends entirely on the window function. However, we can potentially use a rectangular window function if we're very careful about the frequency that we choose for our analysis. And before I provide you with an explanation here, I'm going to once again ask you a question, and this will again help me to contextualize the level to which you are already familiar with this material. I want to ask you, what does each data point in our FFT actually represent? Does it represent the energy at a single discrete frequency? Does it represent the energy summed over a range of frequencies? Perhaps it represents the energy summed over all frequencies. Or maybe it represents something else entirely different altogether. So I'd like you to consider those answers and send them in to me as quickly as you can, please. Again, the survey is anonymous. I just want to take a look at how you respond before I then frame the next part of the explanation. So I'll leave that survey running for you for just a few more seconds now, and then we will look at how you have responded, which I will now do. So let's look at your responses. And I can see that there is a distinct majority of you have responded that you believe that the information contained at each data point in our FFT represents the energy at a single frequency. I can tell you that actually the data points in our FFT represent the energy summed over a range of frequencies, and this is going to feed into the discussion in the next section. So I just wanted to ask you that and clarify the correct answer to the question before we move on. Alright, so let's talk about the notion of an FFT bin and explain why it's called a bin. So we refer to the data points in our FFT as bins, and they actually represent the energy contained in a range of frequencies. So let's look at this example FFT that I produced offline here, and I'm going to look at bin number 176 for the sake of arguments. And in effect, this particular bin, so this data point that we're plotting here at the 176th bin, actually contains or represents the energies contained in this entire range here. So from the leftmost yellow dotted line to the rightmost yellow dotted line. That is a range of frequencies, and any energy that appears over this range is effectively summed and represented by that point there at bin number 176. So that's why we call it a bin, because it's not a discrete frequency, it's a range of frequencies represented by a point in the middle of that range. And that brings us on to the notion of what we call a bin-centered tone. And if our signal frequency is precisely aligned with the absolute dead center of our FFT bin, it turns out that we actually can use a rectangular window function for our analysis. So if we go back to our previous example here, showing you the 176th bin, if we align our signal frequency, so we adjust our signal generator so that its frequency is precisely in the middle of this bin here, which happens in this case to be 1031.25 Hertz, we can actually use a rectangular window function for this very specific tone frequency. It does require that the analysis is synchronous, so in other words, our clocks, if it's a digital system, have to be running at the same rate and synchronized together. And just to help explain this a bit further, I think I'm going to show you another demonstration here. So once again, I'm using exactly the same measurement setup, using the D-Scope Series 3 hardware and software, and this same D to A converter FX unit that I have in the loop. Okay, so let's take a look at this illustration here. Now what I've got at the moment is a sine wave, again playing at -1 dB relative to full scale at a frequency of 1000 Hertz. And you can see that we have the same result as we had before, not a terribly useful result for audio analysis. But if I choose that magic number, that 1031.25 Hertz that I've just explained to you, something rather interesting happens, and you can now see that I have a perfectly clean delta function in my FFT. If I position a cursor here at the center of the bin, so at 1031.25 Hertz, I now only have to move one bin either to the left or to the right, and I'm now in the noise floor. So there is no spectral leakage in this particular example here, provided I set my generator frequency to a bin-centered tone and I use a rectangular window. If I were to switch back to a non-rectangular window, of course my spectral leakage comes back, and if I were to shift my tone frequency very slightly, let's just go for 1030, then again we're back to this condition where the analysis is not terribly useful. So what is a bin-centered tone then? How do we calculate one? Well, let's say that in the general case, we'll call our bin-centered frequency f subscript n, where n is just simply the integer number of the FFT bin. So in order to calculate the 1031.25 Hertz, what I did was said, well, I want to generate a tone at the 20-second FFT bin. So in other words, we take 22, the bin number, multiply by fs, the sample rate, which in my case was 48 kilohertz, and divide by the FFT size, which again in my case was 1024. And that gave me, if you perform that calculation, 1031.25, and that's how I calculated the precise frequency I needed to use to generate that particular bin-centered tone. And this now leads us on to something rather interesting. And what we find is that we can actually use an FFT process, which is actually relatively fast, to perform something quite sophisticated like a frequency response measurement that would traditionally have required the use of a stepped sinusoidal sweep, which is relatively time consuming. And what we can do is actually use thousands of bin-centered sinusoidal tones in our signal generator, all playing at the same time. And if we do that with an FFT with the same number of points as we have tones, then we get a frequency response in a very short space of time. So what I'm going to do is actually, again, illustrate that. And here we go. Here I've got a new file set up to give me a bin-centered multitone. So in my generator, rather than using a sine wave or any of the other options, I've actually selected a bin centers waveform, which is a very densely packed multitone containing a multitude of sinusoidal tone components. In my case, I've chosen 8,000 samples in my multitone, and that gives me just over 4,000 discrete tone components in the real frequency axis. And it sounds a little bit like this. I hope you could hear that. That was a bin-centered multitone, which sounds rather noise-like because it's so densely packed with sinusoids. Now this analysis, this FFT measurement you're seeing on your screen, that was made earlier using quite a large FFT size, significantly larger than the 8,000 points in my generator waveform. If I now use an FFT size that exactly matches the number of samples in my bin centers waveform, then we will find that the FFT is plotted with 1 point at each bin of this bin centers tone, and that gives us the red result here, which is a perfectly clean frequency response. And the remarkable thing about this is the time that it takes to calculate, and I can illustrate this by making some adjustments to my effects unit on my bench here, my D to A converter effects unit, and I'm going to dial in a series of different EQ settings to make some frequency response measurements, and I'm going to do this multiple times, and you'll see just how quickly we can build up a picture of how this device behaves. So I'll just make some measurements for you. And you can see just how quickly this is executing now. I've built up a series of, well, I lost count there, that must be close to 30 traces there, in a very short space of time. That must have taken me around about 20 or 30 seconds at the most, and I've now got somewhere in the region of 20 or 30 frequency response measurements with just over 4,000 points of resolution in each measurement. And if you've ever had to do any frequency response measurements using a stepped sine sweep, then you'll appreciate just how fast this method is as an alternative to that approach. And it's just one of the things that we can do with an FFT once we understand the basics of what it shows us and how to use it. Okay, and in fact there's just one more thing I want to explain about a bin-centered tone before I move on, and this just helps to understand what's happening when we align our generator frequency to these very specific values. So I've chosen a lower frequency in this case, 300 Hertz, just so that when we look at the time domain data, we can see the entire time domain buffer, in this case of 1024 samples. And we can see clearly that when we take the arbitrary frequency of, in this case, 300 Hertz, the capture starts on a zero crossing. That's how I've defined my trigger, more on that later. But it doesn't finish on a zero crossing. And this effectively shows us this discontinuity between the start and the end of the buffer, which shows up as this rather messy frequency response when we use a rectangular window. So I'm going to leave the window function as rectangular, but change the generator frequency to a bin-centered tone. And this one is 281.25 Hertz. And when I do that, I now have this case that we saw before where we have a nice clean delta function in our FFT spectrum, and at the same time you'll see that our analysis of the time domain signal here starts on a zero crossing at the first sample, and at the 1024th sample we end on a zero crossing. So this signal effectively appears to wrap cleanly from beginning to end. It is what we call a synchronous tone, which is equivalent to a bin-centered tone. Okay, so having dealt with some of the basics, let's just come back to this question of how we interpret our FFT data. And we'll go back to the original question of what is the approximate noise floor in this measurement. And we saw that I played a little trick on you. I was expecting some of you at least to say minus 140 dBV, and then I very cruelly went and showed you that that's not actually the correct answer. You fell into my trap, which I cruelly laid. So why isn't minus 140 dBV the correct answer? Well, let's just explain. The problem is that we cannot just simply visually interpret amplitudes from an FFT. If we're talking about a noise type product, we have to integrate energies from a number of FFT bins over the range of frequencies we're interested in measuring. And there's a secondary issue here that we've already seen a bit of, and that is that pure tone energy leaks into adjacent FFT bins. And both of these things mean that it's very difficult, effectively impossible, to just simply look at an FFT and derive things like noise amplitudes, signal amplitudes, distortion amplitudes, just from our visual trace alone. What we find is that we actually need some fairly sophisticated mathematical tools to be able to extract noise and distortion and all those other kinds of parameters that you're wanting to measure as audio engineers. And that brings us on to the tools that we have in the Dscope Series 3 system, but I want to save that for a little bit later on. I want to expand on these 2 points that I've made here because they're quite important issues that we need to be sure that we understand. So, issue number one. I've stated that we have to integrate noise energy over a range of bins in order to be able to say accurately what is the noise floor when we make a measurement on an audio device using an FFT. And to illustrate that, I'm going to go back to the measurement system, the Dscope Series 3, and show you the same test that we performed last time. Turn the trigger on, and again we can see there is the noise at the lower end of this FFT here that intersects the y-axis at approximately minus 140 dBV, but that is telling us that there is, if you look at the reading here, approximately minus 140 dBV of energy at each and every one of these data points, these bins in our FFT. So in other words, if we want to measure the noise over the range, let's say 20 Hertz to 20 kilohertz, what we have to do is, well, first of all, remove the fundamental and all of the harmonic distortion products using this perfect brick wall notch filter or series of brick wall notch filters, but then we must integrate the remaining energy over these other frequency regions, and when we add up all of those contributions, the result is here, minus 111 dBV, not the minus 140 that we may have thought was the correct answer. So that explains how we go about integrating noise energies over a range of FFT bins. Let's come back to the second issue now, where I said that pure tone energy leaks into adjacent FFT bins and that we need to take account of that. So once again, I'm going to go back into my measurement system here because this is best illustrated with a live example, and we will discuss spectral leakage. So just to recap, if I have a bin-centered tone frequency, 1031.25 Hz, and I use a rectangular window function, when I position my cursor here on my tone component, remember it's 1031.25 Hz, there's my frequency reading down here, bottom left. My amplitude reading is showing me effectively -1 dBFS, and in fact that's just slightly off because my reference has drifted just slightly. So if we put 0.962 in there we go, we'll see that we have exactly -1 dBFS of energy at 1031.25 Hz, which is exactly what we'd expect. Now, if I switch to a Prism 7 window function here and change to 1K, so we're talking about an arbitrary tone frequency of 1 kHz for which we know we need a non-rectangular window function to make a sensible measurement. You can now see that the energy here measured in this bin, the nearest bin to 1 kHz, is now reading -1.26 dBFS. Now, this is not an error on the part of the test system because this is a very tightly toleranced, calibrated measurement system, but it's showing us 1/4 of a dB of error at the tone frequency, which is quite significant. And the reason for that is that the energy is leaking into adjacent bins, and we therefore have to integrate the energy over this entire range of, in this case, ±7 bins if we want to put an accurate number on the energy contained at 1 kHz. So that again illustrates why you can't just simply look at the FFT, put a data point or a cursor on this data point and say, yes, that's -1.26 dBFS, because we know now that it isn't. We have to allow and account for this extra energy that has been lost or leaked into adjacent bins. And there are a couple of ways of doing that. The numerical processing tools in the Dscope system that we'll see a little later do that automatically for you. So if you ask for noise at 1 kHz, it will allow for this spectral leakage and include that in the integration. There is also another trick that we can employ, and that is to use this, what we call Prism Flat Top window function. And this is a special window function that looks like this blue trace here on the lower half of the trace window, and that has been specifically designed to minimize the picket fence effect that we call this particular effect, and it ensures that if we put a cursor on our trace here and the tone frequency is not precisely aligned with the bin center, then our amplitude error is going to be less than 0.05 dB. So that is quite a useful trick to know if you want to be able to read these values directly, or read RMS energies directly from your FFT traces. Okay, so hopefully that clears up the earlier question of how to interpret data from the FFT, and the answer is you can't. It's not very easy, and we need some more sophisticated numerical processing tools to do that for us, and we will talk about that in the final section. But before we get there, I want to talk about how we optimize the resolution of our FFT to give us the highest possible visibility of the low-level noise and distortion and crosstalk and intermodulation products that we're interested as audio engineers in analyzing. And once again, I would like to involve you and would like to pose a question to you. What techniques do you think we can use to increase the resolution of our FFT traces when we're considering continuous audio tones, sinusoids in particular? And I've given you 5 different options. Those of you with a PC will see these options on your screen. Firstly, we could increase the FFT size, we could decrease the sample rate, we could use some averaging, we could increase our audio level, or we could use a larger screen. Which of those options do you think will help us to improve, enhance our FFT resolution? I'd be grateful if you could select your options as quickly as you can, and in just a second we will once again take a look at the results of our anonymous survey, and I'll give you just a couple more seconds to consider your options. Okay, let's bring that survey to a close and take a look at how you have responded. And what I can confirm is that all 3 of the top 3 options in this list are potentially valid ways of us enhancing the resolution of our FFT. And a good majority of you correctly identified that increasing the FFT size will help. Decreasing the sample rate may be counterintuitive, but that does also increase our FFT resolution. Averaging, again, can help our resolution. Increasing the audio level doesn't enhance our FFT resolution, although it may increase our ability to see low-level distortion products as we drive our audio device into a non-linear region of operation. So I'm not going to count that as a means for increasing our FFT resolution, and certainly using a larger screen, whilst it may make it easier to see, doesn't give us any mathematical enhancement over the data that we already had. So the top 3 results in this list are the ones I was looking for. Okay, so let's expand on this and explain. Right, so just to summarise then, we can increase our FFT size to increase the resolution of our FFT. And it's important to note that this is really more valid for sinusoidal or continuous tones than it is for transients. If you're looking for a transient event, then really if you make your FFT size too large, then you run the risk of the total noise in your FFT capture exceeding or at least approaching the energy in the transient event. So you need to be a little bit careful if you're talking transients as opposed to continuous tones. But for the purpose of what I want to discuss, increasing your FFT size is a good method. Decreasing your sample rate, as I said, may be counterintuitive, but I'll come back to that and explain how that helps us. Frequency domain averaging, time domain averaging. We have 2 averaging options that I'll discuss in a little bit more detail. Both of these can potentially be used, but we need to be careful, particularly with time domain averaging, because it does have an impact on the noise measurements, and if that's what we're concerned with, then we need to be careful not to use time domain averaging. And we can also use combinations of one or more of the above to help us. So let's talk through these in turn. Well, the first one that I wanted to talk to you about actually was decreasing sample rate, because that, as I said, and as we saw from our responses, may be counterintuitive. That decreasing the sample rate increases our FFT frequency resolution. Why is that? Well, the Nyquist limit is half the sample rate of the digital rate that we are collecting our samples at for the purposes of FFT analysis. And as I said very early on in the presentation, our FFT data is distributed in 2 to the n-1 bins, and it's distributed from DC 0 Hz up to the Nyquist limit. So here's a very crude representation of an FFT with a small number of data points distributed from DC up to the Nyquist limit, or half the sample rate, fs over 2. If I now decrease my sample rate, in this case by a factor of 2, I have reduced my sample rate by a factor of 2, and therefore my Nyquist limit reduces by a factor of 2. And if I leave everything else the same, including the FFT size, then I end up with the same number of FFT bins or data points, but they are spread over half the frequency range in this case. So we actually see that we increase our frequency resolution by decreasing our analysis sample rate. Okay, this one is presumably a little bit more intuitive because we've already seen that most of you have got this correct, that increasing the FFT size increases our frequency resolution. And what also happens is that every FFT bin now contains a narrower range of frequencies and contains less noise, so we see what we might call our noise floor appear to reduce when we use a larger FFT size. And let's just show you that in the flesh. So once again, I have an FFT measurement here. I'm using a 4096 point FFT, and that gives me this live result that we're seeing in red. I'll just turn the live trace off, live time domain trace, so we can see this more clearly. So this is our FFT trace in red at 4000 points, or 4000 lines you may sometimes hear reference to. I have a copy of that here in yellow. Now let's see what happens if I increase the FFT size to 128k. And the first thing you notice is that this is now going to take quite a bit longer. It's actually taking us longer just to acquire the audio samples, and then the algorithm itself takes longer to implement because we have a larger FFT size. So it takes longer, but in return for that longer calculation time, we get finer resolution in the frequency domain. So for example, these intermodulation products either side of our fundamental here become easier to see. In fact, we couldn't even see them at all before. And we appear to get this reduction in the noise floor. And of course, the noise floor hasn't changed at all. Just watch this measurement here. This is my noise, minus 81 dBu. If I go back to a 4K FFT, we've still got minus 81 dBu. The noise is still the same, but every data point now represents a narrower range of frequencies, and therefore we get this apparent drop in the noise floor. As I say, the measured noise stays the same, but the visual information becomes easier to interpret. Okay, so we've seen there's a trade-off between the FFT size and the execution time, so we may be tempted to try and limit the number of points in our FFT, and that means limiting the amount of time that we wait to collect our audio samples. We need to be a little bit careful, because in order to have meaningful data down to our lowest frequency of interest, and in order to obtain the resolution down to the lowest frequency spacing that we're interested in, we have to ensure that we have a minimum of one cycle of audio data at the lowest frequency that we're interested in. And going back to the reciprocal nature of time and frequency, that tells us that, for example, if I want to measure down to 2 Hz, or if I want to have an FFT with 2 Hz spacing between bins, between data points, I need to ensure that T equals 1 over F. F is 2 Hz in this case, so I need at least 500 milliseconds of audio to give me at least one cycle. And if I'm working at a analysis sample rate of 48 kilohertz, that means I need half of that, 24,000 samples of audio data, to give me resolution of 2 Hz. And the nearest power of 2 is actually 32, so that would mean for those conditions I would need to use at least a 32K FFT. Okay, now let's talk about averaging. And a number of you have correctly identified that averaging can help us, and I've already clarified that. Let's take a look at how this works. Firstly, I'll talk about frequency domain averaging. And what we do here is we take a number of successive FFT measurements and we average the RMS power in the frequency domain at each bin of those FFTs. And importantly, this does not affect the total RMS noise energy. It stays constant no matter how many averages you run in the frequency domain. And again, this is easier illustrated with a live measurement. So let's open this file here. And once again, I've got my 4K FFT of a 1 kilohertz tone, and the noise is currently reading minus 81-ish dBu. If I now, I'll show you my copy there in blue, if I now turn on FFT buffer averaging, my red trace now cleans up considerably. This bin-to-bin variation is averaged out, and we see a much cleaner looking FFT. Crucially, the noise has not been affected, so we can still make valid calculations on the THD plus N, or the N, the noise contained within this signal, after we've performed this averaging. And this averaging helps us potentially to see some of these higher order distortion products that may be otherwise masked by some of these bin-to-bin variations. So frequency domain averaging can be quite useful and can help us see those low-level components more clearly. Time domain averaging is also helpful to us, and the reason it's helpful is that it actually reduces the amount of uncorrelated noise in our capture. So this is useful for looking at low-level components that are not noise. So for example, harmonic distortion products will be more clear to see if we can remove some of the uncorrelated noise from the measurement. And what we do in this case for time domain averaging, we ensure that we have an appropriate trigger condition, in this case zero crossing, so that when we sum up multiple passes or multiple captures in the time domain and perform an average, the signal, the fundamental, is unaffected. But the noise, which is uncorrelated, tends to cancel. We get phase cancellation from one pass to the next, and that actually reduces the noise amplitude prior to the FFT calculation. So let's look at that. I'll open my example file here. And in this case, again, I've got a copied measurement here in yellow at 4K resolution with no averaging. Watch this noise figure here of minus 81 dBu and watch what happens to the red FFT trace when I turn on sample buffer averaging. And again, I've just chosen 16 for the sake of argument. Let's turn this on. And you'll see that now the noise floor has dropped. Haven't changed the FFT size. This is a genuine reduction in the noise floor. And you'll see that the noise has been reduced by about 12 dB. You get about 3 dB of reduction in noise level for every doubling of the number of averages. And this can be very useful because now we can clearly see some of these higher order distortion products that were really very difficult to discriminate or even see at all in the presence of the noise in the first case. So this is very useful for picking out low amplitude distortion and crosstalk components by removing some of the noise that otherwise masks our ability to see them. But if you want to measure noise or THD plus N or anything else like that, then this is an invalid method because you're artificially lowering the noise in the time domain before you perform the FFT calculation. So there is a health warning here. And finally, we can choose to use a combination of any of those things that we've just talked about for increasing our FFT resolution to give us potentially very, very minute low-level detail in our FFT measurements. So what I'll do here is go back one final time to my measurement system, and what I'm going to do, well in fact I did this offline because this is going to take some time to execute. I've deliberately chosen the lowest possible sample rate for my high resolution measurement. I've used both sample buffer and FFT buffer averaging, so this is averaging in the time domain and in the frequency domain in a 16:8 averaging matrix. And I've also chosen a very large FFT size, in this case 128K, and of course this took quite some time to execute, so I'll show you the measurements here. This was our original measurement in yellow, where we were struggling even to see the intermodulation products either side of the 1K tone here, and we were certainly struggling to see distortion products above about the 8th harmonic. Well, in this case, the blue measurement, the very high resolution FFT with lots of averaging and a low sample rate, we can now see very, very low level intermodulation, noise and distortion artifacts that we weren't able to see in our original measurement. So it just shows you how you can enhance your ability to see these products. And in fact, I should clarify that the noise has been partially averaged out. So this is really for looking at the correlated distortion and crosstalk products. Okay, so let's now put this all together. We've discussed a lot of the background theory. We've seen some illustrations to help contextualize the issues that we've been discussing. Now let's talk about how we put this all together and actually make some real-world audio measurements of the kind of parameters that you've all said earlier you're interested in measuring, like, for example, THD plus N, THD, N, crosstalk, and so on. This is where we come to the smart FFTs, the FFT detectors that I referred to briefly earlier on. So just to summarize them, we've seen some of the difficulties in extracting meaningful numerical data from our FFTs. We've seen that we have to integrate energies over a broad range of frequencies when we're looking at noise type products or any other broadband components. And we've also seen that even for discrete sinusoidal products that are only present at a single pure tone frequency, we get leakage into adjacent FFT bins that has to be mathematically accounted for if we want to accurately measure the amplitude of these signal or distortion products. And that is where smart FFTs come in. Smart FFTs to the rescue. So what are these things? What do they do for us? Well, these are software-based instruments that reside uniquely in the D-Scope Series 3 measurement platform that I've been using for my illustrations today. And they do the following. They perform our numerical integration to allow us to measure wideband products like noise. They actually automatically account for the precise number of bins of spectral leakage introduced by whatever window function you want to use for your FFT. They allow us to implement analysis filters and weighting filters to perform measurements like THD plus N and noise and crosstalk and all those other things we've talked about. And they also allow us to perform measurements using functions like THD, individual harmonic distortion products, noise in the presence of signal, that you simply can't do with conventional DSP or analog filters. And if that weren't enough, we can also implement our own arbitrary user-defined analysis algorithms to trawl through the FFT data and return whatever kind of audio analysis results you might imagine that you might want to do in the future that perhaps isn't a standard audio measurement today. And on top of that, we can actually have up to 40 of these dual-channel software instruments running at the same time, giving us multiple different measurements derived from our FFTs, all at the same time, updating live in real time. So let's just take a look at its architecture before we see a practical demo of how we can use this to give us meaningful, useful measurements from an audio device. So first of all, we have a trigger condition, and I've talked briefly about this already, and this defines the point at which we start collecting time domain audio samples. And having collected however many thousand samples we want, we then implement a window function, followed by an FFT process, at which point our trace display is updated, and then as a post process we have the option to configure a number up to 40 FFT detectors, or smart FFTs as we know them informally, to perform the numerical calculations for us. So the trigger modes, this is something that you need to be concerned about if you're actually making an audio measurement, and I'll just briefly run through the kind of trigger conditions that you might want to switch between depending on the precise scenario that you're involved with actually measuring. So in a continuous case, this simply says give me an FFT as soon as you can, the trigger fires, and we measure one. Zero crossing, that's something I've used extensively throughout today's presentation, and is in our system it's the default trigger condition and allows us to ensure that our time domain trace is held static effectively in the time domain. We see the waveform at the same phase in the cycle for a periodic signal every time we update the trace window. But we could trigger our capture on some kind of threshold detection, perhaps detecting some kind of transient that might be indicative of a fault in our system, for example. We might want to enforce an equal to condition if we're looking to trigger on a particular digital word, whether that be a sync word in a AC3 stream or some particular sample amplitude that's problematic or signifies the onset of a particular event. We might want to trigger our capture at that point. We might want to be looking for dropouts or glitches in an audio system, in which case you might set up your analysis to trigger at a distortion limit breach, for example. You might simply want to use a non-periodic waveform and you want to trigger the capture at the start of that waveform every time it repeats. Or you may have some kind of other user-defined condition, and you may want to offset your trigger with respect to the 0 point so that your trigger event appears in the middle of the time domain buffer, not at the start. These are all things that I'm not going to dwell on in any more detail than that, other than to say these are the kind of things that you need to consider when setting up the trigger prior to the FFT process, and you then need to think about what window function you want to use and the parameters for the FFT, like the FFT size, the sample rate, etc. So this is my final practical illustration for today, and I'm using exactly the same setup as I have done throughout. I'm measuring my D to A converter effects unit using the digital input port and measuring its connecting a signal to its digital input port and analysing its analog output behaviour. So let's go into this last example then, and this is a live sort of practical illustration of how you can use these numerical post-processing tools to get to the numbers, to give you the figures for how your device is performing without you having to somehow visually interpret this FFT data, which, as we've already seen, is very difficult or impossible to do depending on what it is that you're actually trying to accomplish. So in our system here we have the ability to define a new smart FFT, a new FFT detector, and choose from any one of a wide range of standard functions like amplitude, crosstalk, gain, intermodulation, distortion, noise, THD plus N, and so on. And what I've done is configured about 10 or 11 of these to give me a number of different results, and I've put the readings on the screen here. So the first reading, this is THD plus N. A number of you have already quite clearly stated you're familiar with this, so I'm not going to dwell too much on the detail, other than to say that that is calculated by implementing this weighting filter in the digital frequency domain. So this is just simply a weighting filter applied to the FFT data, also with a low pass and a high pass filter constraining this to the 20 Hz to 20 kHz analysis bandwidth that we're interested in, and giving us the result here, minus 83.5 dB relative to the fundamental. Okay, that's all very well, but it's of little practical value other than to say whether or not your circuit is behaving as you expected. If that value is higher than what you were expecting, the FFT gives you some data, but as we've already seen, it's very hard to discriminate whether you have a noise or a distortion problem, because you can't actually easily put a noise value on this FFT trace. So what I've done, I've got two more readings here, one measuring THD and one measuring N. So we've isolated the noise and the harmonic distortion as two separate quantities, and that has been done like this. The THD measurement is accomplished simply by including each of the first 19 harmonics above the fundamental, so up to the 20th in this case, and you can define that number to be whatever you like. So we're applying a series of 20 perfect brick wall notch filters, showing us the sum of all of these distortion products and presenting it here as a THD reading. Likewise, we have a noise reading, and that is simply windowing out or notching out the fundamental and all of the harmonic distortion products and giving us the residual. So now we can clearly see that in this particular example, the THD plus N value of minus 83.5 dB is dominated by harmonic distortion. The noise is about 10 dB lower. And there's no way we could have come up with that numerical analysis from just simply looking at this FFT data. And beyond that, we can isolate the second harmonic, the third, the fourth, the fifth, and the sixth, and we can go on. I'll just show you the second harmonic, for example. That's just simply giving us a brick wall notch filter to analyse the second harmonic distortion amplitude. I've got a crosstalk reading down here, so I've actually, in my signal generator, I've offset the tone frequencies from channel A to channel B, so I have a slightly higher frequency on channel B, but the filters are selective enough, because they're true brick wall notches here, selective enough to isolate this crosstalk component from the tone component, which is very close in frequency, but we can actually isolate them as independent quantities when both channels are operating. Here I have a 50 Hz mains hum measurement, so this is actually summing up the energy in the first 5 harmonics of the European 50 Hz mains frequency and presenting that as a number. And one final example here, I've actually got an example of a user-defined analysis algorithm here that we wrote for one of our customers to calculate a precise number for the ratio of the odd to the even distortion products, and that is now displayed in a numerical reading that can have limits applied to it, as you would normally do with a standard audio measurement. So this is just one snapshot of the kind of thing that you might do when you've first built your prototype or received your first samples from your supplier and you're wanting to analyze many of these parameters. This can all be done in real time from an FFT, and these are all updating live, so if I now go to refine my circuit design in any way, I will see how all of these parameters update, and I can track the trade-off from one parameter to the next as I tweak my circuit design. So this is just one illustration of the power of FFT processing and what it can do for you in terms of increasing the speed and your workflow when you're doing this kind of measurement. So a quick recap then. We've already seen that the FFT algorithm is a very powerful tool for giving us very detailed information. Very low-level artifacts can be clearly revealed in an FFT analysis that we simply can't see in our time domain signal. And as I have emphasized several times, we can't simply look at the FFT data to obtain meaningful, precise numerical measurements of parameters parameters such as noise and distortion and crosstalk and so on. We need more sophisticated numerical processing tools, and I've just in that last example shown you how you can use this particular measurement system to do all of that number crunching for you, factoring in the effect of whatever window functioning you have used, and allowing you to do averaging and customized triggering according to whatever it is that you need to do. So developing the idea of the FFT then, well, that goes beyond the scope of what I'm going to discuss today, but one example is multitone analysis, which relies very heavily on FFT processing to give us not just individual sinusoidal results, but we play a number of tones at the same time to give us things like harmonic and intermodulation distortion as a function of frequency, crosstalk as a function of frequency, frequency response, all of this from a single FFT capture. Likewise, electroacoustic analysis relies very heavily on FFT processing when we're talking about making gated impulse response measurements to remove room reflections from our loudspeaker measurements. These are two examples where we go a step beyond what we've done today in terms of FFT analysis and really get to exploit the power of FFT processing. And there are many other applications besides, and these things are things that go beyond the scope of my discussion today, but we have covered a great many of these in our past series of webinars that you can access at prismsound.com/webinars, and you're free to download whichever webinar recordings are relevant to your specific audio applications, and there are a few examples on the screen there of the kind of things that we have talked about in the past. So thank you all very much for your time and attention. I sincerely hope that you found today's presentation interesting and useful, ultimately. I hope to see as many of you as possible on a future Prism Sound webinar. But for me, Simon Woolard, for now, I'm going to say one final thank you to you, the audience, and I will bid you goodbye for now. So thank you and goodbye.